Welcome back. Let's look at a geometric interpretation of the scalar triple product, which is also the same as the 3 by 3 determinant. Um, we know that if theta is the angle between the vector A and the vector B cross C, then their dot product, which is the scalar triple product, would be equal to the length of A times the length of B cross C times cosine theta. So as a result, we can say that the absolute value of the scalar A dot B cross C is equal to the length of A, length of B cross C times the absolute value of cosine theta. Now the three vectors A, B, and C, which are in dimension 3, if we draw them at the same tail, then these three vectors they span a box-looking object which we call parallelepiped spanned by A, B, and C. Now notice that the vector A and B, they span a parallelogram. The vector AC spans a parallelogram. The vector BC spans a parallelogram. So these three vectors, they would span this parallelepiped, and it turns out that the volume of this parallelepiped is equal to the absolute value of the scalar triple product of A, B, and C. Now, so in other words, if I compute the scalar triple product, I am getting the volume of this parallelepiped up to -1. Now, why is that the case? Why do we get volume from this scalar triple product? Well, let's see. See, we have this parallelepiped spanned by the three vectors A, B, and C. And to find the volume, we need to find the height of the box here. So to find the height, we do the following. First of all, we're going to take the parallelogram spanned by B and C as the base, and so B cross C would be a vector that is perpendicular to this yellow parallelogram spanned by B and C. From the tip of the vector A, which is labeled as the point P, we make a perpendicular line onto this parallelogram. We get a point Q on the parallelogram. Then the height of the box is the distance between P and Q. Now, from the point P, we make a perpendicular line onto the vector B cross C, and then the blue vector right here, this is the projection of A along B cross C. And clearly the distance between P and Q is the same as the length of this projection vector of A along B cross C. So the height of the box is given by the length of the projection of A along B cross C. Now the projection of A along B cross C, that's the same as the absolute value of the component of A along B cross C. And we know that the component of A along B cross C is the same as A dot B cross C divided by the length of B cross C, and we are taking the absolute value here because that's what we are taking it here. So we got the height. So then what's the volume? Well, here, what is the base area? What is the area of the base here? So what is the area of the parallelogram spanned by B and C? And we saw in a previous video that the area of the parallelogram spanned by the vector B and C would be given by the length of B cross C. So then the volume would be the height times the area of the base. So height is the absolute value of A dot B cross C divided by the length of B cross C, and then multiplied by the length of B cross C. So these two cancels out, and as a result we see that the volume will indeed be given by the absolute value of the scalar triple product A dot B cross C. So what we got then is that the volume of the parallelepiped spanned by the vectors A, B, and C is given by the scalar triple product A dot B cross C up to -1. That is, the scalar triple product can differ from the volume by a negative sign, but if we take the absolute value of the scalar triple product, then we would get the volume. Okay, here's an example. Let's say we have the vectors A, B, and C given by 1, 0, 1, 1, 0, 0, and 1, 1, 0. So what's the volume of the parallelepiped determined by these three vectors? Well, it is given by the absolute value of their scalar triple product. Well, we find the scalar triple product, so A dot B cross C. We know that that's equal to the 3 by 3 determinant, where the first row is A, second row is B, and the third row is C. And if we calculate that, we get 1. So that would be the volume of the parallelepiped spanned by these three vectors. Okay, so that's the geometric interpretation of the scalar triple product, and so we will end the video right here, and thanks for watching, and I'll see you in the next video.